All right, here's a problem, an elastic collision problem. You might find this problem on page 212 of your book. It's going to be problem number 3. And you have two soccer balls in this problem. The first soccer ball is moving. I'll use this as the first ball. This is the first. The balls are identical. This guy is moving at 3.5 meters per second to the right, and it's going to hit or collide this soccer ball, which is at rest. So let's say this first guy here is, this ball is going to be in yellow and this one's white. This one collides with this one. After the collision, the yellow one stays still and the white one goes off its merry way at some velocity v, and we want to find out a couple of things here. First thing we want to find out is what is the velocity of this soccer ball after the collision. First it's at rest, now it's moving. Well, how fast is it moving? Well, our conservation of momentum techniques tell us that the total momentum before is equal to the total momentum after. And it's total momentum, not individual, but total. So what's the momentum over here? The momentum is the mass, 0.4, times the velocity, 3.5. This is at rest, so it's nothing. So plus is 0. That's a total momentum before the collision. After the collision, we've got 0.4 times 0 plus 0.4 times some velocity v. We know that we have to set that equal because momentum is always conserved in a collision, whether it's elastic or inelastic. Your total momentum is always conserved. Well, if you look at this, this is going to be 0. So you got 0.4 times v equals 0.4 times 3.5. So immediately you can see that v has to equal 3.5 meters per second. In order for this equation, this is equal to this side, this has to be the solution. So if this one comes to rest, this guy has to have the same momentum as this one before the collision. Now they might ask here, they say, what's the kinetic energy of the ball after the collision? Well, kinetic energy is equal to 1/2 the mass, which is 0.4, times the velocity squared. And that's going to be in joules. After the collision, what's the kinetic energy of this ball? 0, because it's not moving, it's at rest. And that's the extent of problem 3. Let's really quick do another problem. Let's look at problem, well, how about problem number 2? So I'm going to make a little bit of room here. See if I could do problem number 2. We've got a 95 kilogram fullback moving south with a speed of 5 meters per second, has a perfectly inelastic collision with a 90 kilogram opponent running north. Alright, so north-south. Let's just do it this way. There's somebody here. I represent it by a circle. They are 95 kilograms and they're moving south. They have a speed of 5 meters per second. And they're going to have a perfectly inelastic collision with a 90 kilogram opponent running north. So somebody's here, has a 90 kilogram mass, and they're running north. And they're running north at a speed of 3 meters per second. So that's before they collide. After they collide, we're told that we have an inelastic collision, and we're told it's a perfectly inelastic collision. That means they kind of like come together. They're two football players, so they're going to tackle each other, and we're going to have a combined mass of the 95 kilogram guy and the 90 kilogram guy. So this gives us a combined mass of 185 kilograms. And it says, so what happens here? Just after they collide and tackle, what's the velocity? So we're not sure. Is the velocity of these two up or down? I'm going to put it up we're not sure what it is, what its direction, but it's here. This is after the collision. Now we're going to use conservation of momentum. Let's look at conservation of momentum. Before the collision, our total momentum, I'm going to assume that up is positive. Just so that we can do this problem, we have to make some kind of an assumption for direction. Then we have the momentum of this guy is going to be 95. Mass times velocity now. The velocity is going to be minus 5. The momentum of the guy that's running up or north is going to be his mass, which is 90, times his velocity, which is 3, and that's positive because we said upward is positive. That has to be equal to the momentum after. Now the momentum after, we're just going to have one final mass of 185 times some final v. So let's see what we could calculate here, and whether or not what we can get with this v. Now I'm going to do it. I'm going to put this on pause. I'm going to do this for us. Well, actually, I don't have to put it on pause. Let's just do it real quick. We've got 95 times 5 is going to be 475. So this is negative 475 plus this is going to be 270, and that's going to be 185 times v. So if we do this, that's 205. So this is minus 205 equal to 185 v. So v then is going to be minus, that's going to be 205 divided by 185 is going to be 1.1 minus 1.1 meters per second. So our assumption of choosing v after the collision as up was incorrect. We see now that they actually are moving downward at 1.1 meters per second after the collision. So that's how we solve that velocity. Now since this was perfectly inelastic, we know we had to lose kinetic energy, and we could find out how much kinetic energy we lost by looking at the initial kinetic energy. The total initial kinetic energy is going to be 1/2 95. It's going at minus 5 squared plus 1/2 90 going at 3 squared. That's going to be the initial kinetic energy. The final kinetic energy is simply going to be 1/2 of 185 going at negative 1.1 squared. You calculate this, and you could see what the difference is, and I will bet, I'm not going to do it now because we don't have time here on the YouTube channel, but I'm going to bet that the final kinetic energy is going to be less than the initial kinetic energy, as it has to be for an inelastic collision. So this was an example of inelastic collision. All right, see you next.